Hi everyone, and welcome to this video that I'd like to describe two important tests that we use in transformers to find their parameters, the core and the winding parameters. And these tests are called the no-load test and the short circuit test. Why they are called these names, how we can use them to find the equivalent circuit of the transformers and other practical aspects. Let's start. So we'll start with some summary what we have done in the previous video. We talked about the different models of the transformer, and we call this is our exact model. This is the exact model. And then we said that this model actually, this part is the primary winding. So basically, this is the resistance and the leakage reactance of the primary winding. Then we said this is the secondary winding of the transformer. So we have the primary and the secondary, and this is the core. So these are the three parts of the transformer model. Then we said that because this current is extremely small, we can move this part to here and adding the two resistors in series and the two inductances in series, so we get this model. So this R equivalent is nothing but the R in the primary plus a square R in the secondary, and the X equivalent the same thing. It's X in the primary plus a square XS. And here just to remind you, this a square, because we are referring the secondary circuit to the primary circuit, as we mentioned in the previous video. Now, one thing we mentioned here, another justification other than that the current is very small and the error from moving the core from one point to another is it will not affect, but it will reduce a little bit the calculations. But we said that the most important justification for this reduced, this is the reduced model, and this was the first reduced model, is that this is the model that we can measure in using two different tests, which is the no load test and the short circuit test, or the open circuit test and the short circuit test. That is the model that we can actually measure. So let's start with the open circuit test. Now, in the open circuit test, we have two sides of the transformer. There is the high voltage side and the low voltage side. So we always open circuit the high voltage side, and we apply the rated voltage for the low voltage side. What does this mean? For example, if I have an 11 kilovolt by 240 volt transformer. So this is a distribution transformer that changed 11 kilovolt to 240. Now this is the high voltage side and this is the low voltage side. Okay, so I will come to the high voltage side and I will open circuit it. Okay, and then I will apply the rated voltage to this low voltage side. So I will be applying 240 volt from here. Now, if you look down here to this photo of a transformer, this is the low voltage side. So you see here that we are connecting the connection for the voltage, and the high voltage side, these are the bushing for the high voltage side, are not connected to anything, or they are open circuit. Now, what do we measure here? We measure three things. We measure the voltage that we are applying. We measure the current. We call it the no load current, and I will talk about the no load current in a separate video. And we measure how much power that the transformer is consuming at the no load when this is open circuit. And the reason why we call it no load or open circuit, same thing, because there is nothing connected to the other side of the transformer. We're applying a voltage from one side and the other side is open circuit, or there is no load connected to it. So we have three parameters that we are measuring. Now, this is the model of the transformer. So which part this test can be able to calculate or to find the parameters of the transformer? It will be the core part. So the objective of the no load test is to find RC and XM, the resistance of the core that represent the hysteresis and the eddy current loss, and the inductance that represent the magnetization inside the core. So let's see how we can do the calculations. So basically, as I mentioned, we measure three things. We measure the voltage, we call it V open circuit. We measure the current, we call it I open circuit. And we measure the power, and we call it P open circuit. So we measure these three parameters. Okay. And from these three parameters, we want to find RC and XM. So how we do that? We calculate the magnitude of the admittance. The admittance is actually 1 over Z, the inverse of the impedance, by dividing I open circuit over V open circuit. Now, this is only the magnitude, but we need also to find an angle because this is a vector. How to find the angle? Using the power formula. P equal to VI cosine theta. I know the power at the open circuit. I know V open circuit. I know I open circuit, so I will find the cosine theta. And we know that the power factor angle is basically the angle of the impedance. Okay, so theta is nothing but the angle of the impedance, which is in this case this parallel branch. Okay, so I will combine the magnitude and the angles, so I will get the vector of y, of the admittance. So I will have a magnitude which is dividing the current by the voltage, and then take minus cosine inverse. Why minus? Because this is the admittance. If it is the impedance, it will be plus. But because we are getting the admittance, y is equal to 1 over z. So z will have the angle theta, so the y will have the angle of, this is y 1 over z, angle of minus theta. Okay, now the y, the admittance, now when we have two parallel branches, this is why we are finding the admittance. It's basically 1 over RC plus 1 over JXM. So your Y, the admittance of a parallel branch, this Y is equal to basically 1 over RC plus 1 over JXM. And we know this Y, equal to YE of the excitation. So basically your Y will have a real part and imaginary part. The real part is 1 over RC. The imaginary part is 1 over Rxm. So after we calculate the division of I open circuit over V open circuit with the angle, then we are getting the vector value of the admittance. Okay, so this is how we find the excitation branch of the transformer. The question is, can we apply or reverse the test, meaning applying the rated voltage from the high voltage side and not from the low voltage side? Of course we can. However, it is more economical to have a generator that can supply the rated low voltage side than a generator that can supply the rated high voltage side. So this is why we always do that. We always apply the rated voltage to the low voltage side of the transformer, and we open circuit the other side of the transformer. Now let's go to the short circuit test. In the short circuit test, basically, we short circuit the low voltage side. So the low voltage side is short circuited, and we apply a voltage at the high voltage side so that we will have the rated current. What is the rated current of the transformer? Then we will let this current passes by applying, and it's usually a small voltage. Then you will have the rated current inside the winding of the transformer. And how it is done practically, so this is the low voltage of the transformer. We have here, as you can see, there's a bus bar here short circuiting all the bushings, so the bushings are short circuited, and we are applying the voltage, a portion of the voltage that is actually not very high, but we are measuring the current. Our eyes is on the current. Make sure that we have the rated current. So in the previous test, we applying rated voltage, In this test, we are applying rated current. Now, the same point I made uh, about the open circuit test, can we reverse? Can we apply the voltage from the low voltage side and short circuit the high voltage side? Theoretically, I can. Practically, I cannot. Why is that? Because in the short circuit test, I will need 3 to 6% of the voltage to get the rated current. Why is that? Because of the short circuit. So I will need a small voltage to make the current or the rated current going through the winding of the transformer. So if again I use the same example of 11 kilovolt by 240 volt transformer, if I apply the voltage from the low voltage side and short circuit the high voltage side, then I will need 3 to 6% of the 240 volt, which is basically between 7.2 to 14.4 volt, which is extremely very small voltage. It's very hard to control such a small voltage in the transformer. And if I exceed a little bit, I might burn the transformer. Because remember, there is a short circuit there. So there is no much impedance to oppose the current. So if I increase the voltage a little bit, then I might damage the transformer. On the other hand, if I apply that from the high voltage side, 3 to 6% of the 11 kilovolt will be between 330 to 660 volt, which is I can easily control that. I can easily supply this amount of voltage from that side. Now, what is the objective of this? Now I think you figured it out, is to find the series element of the transformer, to find the equivalent resistance and the equivalent leakage reactance, and these two quantities is for the transformer winding. Now, what are the formulas? How we do calculate that? Again, now we measure three things. Again, V, I, and P. So we measure V, we call it V short circuit, I short circuit, and P short circuit. So how to use these formulas? In a very similar way, like what we did in the open circuit test. However, here we will find an impedance other than the admittance because they are in series, not in parallel. So the magnitude of Z from the short circuit test is V short circuit divided by I short circuit. And the angle for that, because again, I need an angle using the same formula that the power equal to VI cosine theta. And now this theta is basically the angle of the impedance, R equivalent plus JX equivalent. So now I will have the total Z, which is V short circuit over I short circuit for the magnitude. And the angle is actually theta. And this will be equal to the R equivalent. So this is in polar format, and here is in rectangular format. This is your R equivalent and JX equivalent. And we know that this R equivalent is nothing but adding the primary resistance plus A square, the secondary resistance when the circuit is referred to the primary, and same thing for the leakage reactance. And this is why we said that in this test we can only calculate the total resistance, the total leakage reactance. We cannot find the individual until we do some more complicated calculations that out of the scope of this presentation.